If you love the freedom that filament 3D printing gives you, especially when pushing towards strong, functional parts that don't snap under stress, then you're always hunting for tough materials. The market keeps introducing new materials, but from the datasheets, it's not easy to understand how that material will actually behave once printed and subjected to real stress. So you end up buying an expensive spool, fighting the printer, and discovering the material wasn't as tough as promised. In a toughness cost map, the most interesting materials are in the top left. Low cost, high toughness. While in the bottom right, we have high costs and weak materials. What if we had a tool to push the market to offer materials in that part of the map? What if you could contribute too? Let's follow this short video and find out how. That's exactly why we built the Tough3d app, a platform that pulls together datasheets from filament manufacturers and structures them into a searchable database for comparing thermomechanical performance. Because manufacturers often skip key data, especially Z-axis tensile strength, also called layer adhesion, we've integrated the outstanding work done by the independent testing lab MyTechFun, which specializes in precisely the toughness metrics we care about most. In the app, the database merges and cross-references OEM data with MTF data, giving you an always updated ranking of the toughest materials on the market, refreshed weekly. Let's walk through a real usage example. First, choose which datasets to use: OEM only, MTF only, or sync, which means materials for which we have both. You can also filter by brand or material family: ABS, ASA, PC, or all of them. The counter always shows how many filaments are active in your selection. Then choose your comparison mode. For OEM data, you'll need to narrow to a few common metrics, since not all datasheets are equally complete. For MTF materials, you get a much richer set of properties thanks to the thorough characterization. Now, let's look at this slider panel. Since each material has strengths and weaknesses, and your application has specific demands in terms of combinations of those strengths, we'll use the sliders to weight each performance factor, to tell the ranking algorithm how much a certain performance is important for our application. CWP stands for Combined Weighted Performance. Go fully custom, or pick one of 4 preset scenarios. N for normal use, R for demanding structural requirements, R2T for high resistance and elevated temperature, and R2T2 for extreme loads and even higher temperatures. For each scenario, you get a real-time ranking of the materials scoring highest against your exact mix of requirements. Since the database includes the cost per kilo for every material, the next step is to normalize performance against price. Hit the performance to price toggle, and the ranking reshuffles into best buy order. Use the config slider to dial in how much you value cost versus performance, from "I want the absolute best regardless of price" to "I want the best mechanical performance at the lowest possible cost." Different applications, different trade-offs. Explore the DNA of each filament through radial charts that make strengths and weaknesses immediately visible, even overlapping multiple materials at once. Below, the table view ranks all materials with the database's state-of-the-art reference in the first row, showing the best values across every metric as a benchmark. To inspect a material in detail, long press on it to open a detail card, where we see a radial chart with a performance declared by manufacturers compared to MyTechFun measurements. Both the numbers and the curves follow a color code: cyan for MyTechFun, orange for OEM, blue for the state-of-the-art. Below, we also have the percentage reference relative to that benchmark. Then below, we have links to the technical datasheets, both locally and on remote repositories. Let's try opening them. Print guides are included, along with slicer profiles when manufacturers provide them. There is also a link to the MyTechFun YouTube video. We then find the price per kilogram and a small 3x3 matrix, a synthetic map of performance versus cost. Top left means high performance at low cost, the most interesting zone. Bottom right means low performance at high cost, the least interesting. At a glance, you can see exactly where a material stands. There is also a direct link to the vendor's shop. We then enter the community section, where users who manage to fine-tune reliable printing processes for a given material on a specific printer can share their files and earn credits in various forms. Files can be uploaded in various formats, both from local storage and from sharing platforms. By tapping the ENG mode toggle, engineering mode, we can see tensile strength values in the XY direction as a bar and tensile Z as an orange line inside the bar. We can move the sliders to raise or lower the desired stress threshold, and materials that don't meet the requirements will disappear. We can sort by XY or by Z in descending order. It's interesting to see at a glance how isotropic a material is. The closer the orange line reaches the base of the bar, the more balanced the material is. The same applies to shear and torque. Further down, we find a tensile XY versus tensile Z chart. The best materials sit in the top right corner, maximum XY tensile and maximum Z tensile. The trend line is also shown. Everything updates, dynamically changing the selections. Finally, rotate your phone to landscape to get the full power of the Frontier chart. The axes are performance on Y and price on X. The most desirable zone is top left, maximum performance at minimum cost. Distribute all filaments on this plane. Then, for each price point, climb vertically to find the highest performing material for each price. Let's connect those points and you get the Pareto optimal frontier, the dominant materials. This frontier updates for every severity scenario: N, R, R2T, R2T2. We can see that around 500 materials are dominated in terms of performance to cost ratio by about 10 filaments, and also that under $70 we find the best ones that outperform even much more expensive options. If we zoom out and look at all materials, we can see many points at higher cost but with equal or lower performance. If we set a lower cost limit, some dominant points drop out, and we always have one point that represents the best option for that cost range and temperature. So why spend more? We understand this when we increase the severity of use, for example, by raising the operating temperature. As we increase the demand, some points drop out, even dominant ones, and the frontier changes. We can observe how the materials that disappear, shown in red, increase in number, and the ranking of brands with the most surviving materials, shown in green, also changes. As the temperature rises, the usage scenarios update automatically, and dominant materials at higher price points appear: $275 and then $550. Let's now go back to scenario N and temperature below 60 degrees Celsius. We can inspect each point, both dominant and filtered. For the filtered ones, we also have an indication of the price correction needed to jump onto the dominant curve. If we want to recover a range of materials below the dominant ones by lowering this threshold, some materials come back, also with a more or less significant price correction. We can also have the system calculate for all these points the right price to become dominant, RPD. Let's take, for example, the case of Sunlu PA6CF, priced at $38. To become dominant, it would need to cost $28.4, with a correction of about $9. It's more clear now how this tool and the users can push the market towards best performance at competitive and cost. On the left, a brand ranking shows which manufacturers have the most survivors, green numbers, the killed in red. We can move the sliders to raise the temperature threshold, and we will see a strong filtering effect. It is also interesting to see the distribution areas of filaments by brand on the left and by material family on the right. This map is useful for spotting which polymer blends are most promising and worth further development investment. To wrap up, Tough3d is becoming a platform that connects the materials world with the evolution of printing hardware. We're living through a breakthrough moment. Tool changes, actively heated chambers, integrated dryers. The conditions for actually exploiting tough materials are finally falling into place. And the community, its passion and cleverness in finding the perfect match between filament and hardware, is a fundamental part of this. Thanks to the analyses in Tough3d, we can bring these three factors together. The outcome of this platform is a shared direction for the whole ecosystem. Filament manufacturers understand which materials are most demanded. They are pushed to provide more complete data, and the user know exactly what to buy. Printer makers see what their users and materials actually need, and the user understands which hardware to buy. The result is a push toward parts that are not just tougher, but repeatable, thanks to tested, community-validated print profiles built on a broad base of real-world experience. Join the platform. Start today.